Okay, so I'm Brandon Massoni, and I'm going to be talking about titanium as it's used in additive manufacturing. And so this picture is just a picture of raw titanium. It doesn't, I don't know. Did anyone see the flash on it?
If it's recording, it says stop, so it's recording. What? It says stop. It gives you the option to stop the recording, which would tend to indicate that it is currently recording. Yeah, stop. What about volume? Then it should be fine. If the last one was fine, it should still be working. Sorry.
Okay. What? So some of the significant properties of titanium: high strength to weight ratio, it's corrosion resistant, biologically compatible, non-magnetic, and it's resistant to galvanic corrosion. Specifically, that last one is important when you're talking about pairing it with carbon fiber composites, which makes it a choice over, say, aluminum, uh, which will corrode with carbon fiber. And so some typical applications for this are biomedical and aerospace. And so there's a picture of a jaw that was 3D printed with SLM, and an Airbus part that was printed as well. Yes? So it has to do, galvanic corrosion has to do with the electricity flowing between the dissimilar metals, or yeah, so between the carbon fiber and the aluminum. But since one of the properties of titanium is similar to carbon fiber, it doesn't have that large change, so that electricity doesn't flow across it.
So this is when the composite is connected to titanium is connected to steel, or
So when the composite is directly touching the metal, that's when the galvanic corrosion will occur.
You'll also see that a lot in like boats and stuff. If you're connecting two dissimilar metals together,
That's where they use the sacrificial nitrogens used.
well, zinc. Usually zinc. So most boats have zinc on the bottom, and at least a few big chunks, because
yeah,
that way dissimilar metals won't corrode.
yeah. So metal to metal. Are you familiar with the electrochemical series at some point? So you have noble metals right at the top, and then you have metals that slowly go down the list, and so the ones at the top will not get precipitated by the other material. So for instance, if you throw iron filings into copper sulfate, you will precipitate out the copper. And that's like a high school chemistry thing that so there's a series of what will get eaten up, or dissolve into, or go into solution, and what will remain intact as a metal. Right? So if you had like a steel fluid, right, in connection, in conjunction to a copper sulfate, or a copper salt, or copper in a connected somehow with some moisture present, slowly the steel will get corroded, the iron will get, so that's an analogy between the iron filings going into solution and the copper particles getting precipitated. So basically, the relative position of titanium relative to aluminum is higher in the C, and so aluminum will. But I thought, I don't know what the carbon fiber does. I mean, apart from carbon fiber being an electrical conductor of adhesion, unless there's
That's what
one
it's
more
doing.
material involved.
I don't know. I didn't look that much into it,
Okay, good.
but
Probably just weakens the bond between them, making it corrode.
Yeah, you don't want to mix carbon fiber and steel.
probably not.
Probably again that galvanic.
Probably the same thing. Titanium is considered one of the noble metals, and for both biomedical and aircraft, which is mostly what titanium is used for, the most common alloy is on the next page. Ti-6Al 4V, which is 6% aluminum, 4% vanadium. And so these are some of the properties of that. Comparing powder from RCAM, that's what these are taken from, compared to some rot properties. And they can vary quite a bit, but what you can see is the ultimate strength and yield strength tend to be lower, and the elongation, which is a measure of ductility, tends to be lower. So these are ranges that I've found, and it's matching one to another doesn't necessarily mean that that's what the range are. So the research studies I'll go into later address some of these different material properties and how we can change some of them. So RCAM is one of the vendors of titanium alloy, and they have a wide range of particular titanium alloys available, including Ti-6Al 4V. And then also Purus, which is based out of West Virginia, and they have a range of this ETI titanium alloys, which has this additional, they have an additive in it that somehow improves the strength and stiffness by about 25%. But it didn't say what it did to the ductility, so I don't know. Probably not good. So here's the case study one, the jaw implant. So what's important about this is it has articulating joints, it has some cavities to promote muscle attachment, and grooves to direct the regrowth of nerves and veins. And so what that entails is just there's a lot of complexity to this part, and why it was beneficial is it's unique to each patient. So if you have one base design that you just fit to everyone's jaw, you can do that with this, and you only have to make one. It only took a few hours to print, and it is 1/5 of the time in surgery, which is huge because it fit with the way it was supposed to the first time, and there was no adjustment necessary. Where that's some issue they run into with other methods. So that by itself is huge. Case study 2 is this Airbus part. It's a cabin bracket / hinge, and so this was shown because it was topology optimized, which is an interesting method of moving material to the load paths so you can have a lighter part. And traditionally this might be very difficult to machine or just straight up impossible to machine, whereas if you additively manufacture it, you can create these lighter weight parts and reduce stress concentrations as well. And so there's also less waste in this process. So research study 1 was microstructure and mechanical behavior of titanium Al4V produced by rapid layer manufacturing for biomedical applications. And so this was looking specifically at EBM and SLM. And they compared these materials to wrought and cast. And every study I've looked at has had different material properties for wrought and cast. So I'll just use whatever ones they've selected in their particular study here. But what they show here is that they could get yield strength and ultimate tensile strength that are similar or superior with both EBM and SLM to the wrought material. And also you can just see that the cast material is generally worse across the board there. And then elongation was actually better for EBM than it was for wrought, which means that it should be more ductile. But for SLM it was lower, considerably. So this has a large impact on whether you can use titanium. The ductility is rather important. It's similar to why people don't use castings, because they tend to be, I don't want to say brittle, but they don't bend as much.
So
They're brittler. So the second research study I had looked at this issue of ductility. with selective laser melting via the situ martensite decomposition. So they were looking at the microstructure, and they created these different test samples, and then looked for the changes in elongation and the necking there. So can ductility be improved? And what they found out was that it could, and they had a few ways that they could do it. The first thing they did was the layer thickness laser beam, FOD, which is, I forget what that is, energy density. They can all be tuned to create this ultrafine laminar alpha-beta structure, which is something that this research paper identified as being beneficial to improve ductility. And supposedly, according to the research article, which was in this year, this is the first time that they've looked at this alpha-beta structure as a possibility. So what this ends up looking at, we then have the heat treatment as low as 400 degrees Celsius can lead to a near complete transformation to ultrafine laminar alpha-beta structure, and then that can yield 1100 megapascals yield strength, and a large elongation failure up to 11.4%. So that's now comparable to the rot properties that we saw on the previous slides. And so they show that over on the graph on the right. It's total elongation to failure on the x-axis and yield strength on the y-axis there. And the ones they've highlighted are SLM and what are the other ones?
On what order of magnitude are these layers? So is it 10 micron smaller?
Oh, I'd have to look at the paper, but they had the list of parameters for all the different stuff in there.
Just wondering if it was like orders of magnitude smaller than typical.
Yeah, I didn't take a look at that.
No, I mean, you're sort of limited by the particle size anyway, and for many of these things, they're about 40, 50 microns.
Right. There's a bunch of studies that they're doing 20 micron. Things like that.
So the previous in your previous slide, does the layer thickness S362?
Hmm?
So in your
Oh,
in the
60 micron?
60 micron.
Okay, so in this particular example, it was 60 micron in this picture. And those are my references.